Let's define the probability of error for this scheme up here. Probability of error. Lambda I is the probability that my guess, W hat, based on the random sequence yn, is not equal to I. Given that I meant it to be equal to I, that it's given that the input sequence xn is little xn of I. And this is defined for I equals 1 up through m, which I'm thinking is 2 to the nr. But, okay. So that's the individual probability of error. You know, oh, you mean not equal to I? Yeah, thank you. Yeah. Let's see. So lambda super n is just the max of lambda I over I in 2 to the nr. So it's the worst code word. You know, wouldn't it be great if you had a code that sent at capacity any integer you wanted, but except on one of the integers you wanted to send, it asked you to send the same code word as for another, which means looking backwards, you have nothing in y to distinguish the x's because the x's are indistinguishable for I equals, say, 1 and 2. So your probability of error is going to be a half when you receive, when you send a 1 or a 2. The conditional probability of error is going to be a half. Well, that's terrible. So here you are, you're at capacity, you're happy. But let's suppose your message is like help, and the second message is don't help. Well done. That would be a disaster. In any case, so we're interested in the worst case here, lambda n. And then PE super n. Now it's tempting to call this a probability of error. It's 1 over m, summation of lambda I, from I equals 1 to m. Sure, it is. If each of the integers is equally probable, this is the overall probability of error. But I want a code book that's a little bit stronger than one with a low average probability of error, where help and don't help can only contribute 1 over m to this, and therefore probability of error can still be small. But I want the worst case to be good. So lambda sub I is always a conditional probability of error, but PE super n, which you'd like to call a probability of error, is only a probability of error if the input words have indices, if the indices are uniformly distributed. All right, now let's define rate. Definition. The rate R of and MN code is R equals log M, the number of bits in the set of indices I send, over N, the number of bits per use of the channel. So this is in bits per use, or bits per transmission, if you wish. Definition. R is achievable if there exists a sequence of codes indexed by the block length n Well, I'll be specific. Two to the NR N codes with maximal probability of error, lambda super n, going to 0. Great. Now that's a good definition of achievability. It says, for block length n, you're sending R bits per symbol, and you have a maximal probability of error. You're looking at your worst code word, and that probability of error goes to 0. You will have noticed that if lambda n goes to 0, then certainly PE super n goes to 0, because each of these terms will be going to 0. And this is the average of those. Definition of sort of operational capacity. C equals the supremum of achievable rates. Suppose I could say, I'm going to make a comment about supremum. It means maximum. But C, let's suppose that R less than R naught is achievable, but R equals R naught, or certainly worse, R greater than R naught is not achievable. So you say, oh good, I get any rates up to R naught. You know, I can achieve any of those rates. What's the maximum rate I can achieve? Well, sorry, I can't tell you, because I can't. I'd like to say R naught, but R naught is not achievable. I just told you. Only R arbitrarily close. So that's what the supremum is. So C is the supremum of achievable rates. When the maximum exists, the supremum is the maximum, and when it isn't, it's sort of the maximum of the closure. All right. So now we have two different definitions of channel capacity. One is max of I of x, y, and the other is it's the highest rate at which you can get information through that channel with probability of error arbitrarily small. Well, that's obviously the question, and C equals max of IXY is the answer. So I gave the answer first because it was fun. As usual, we gave entropy and then we did data compression. We gave capacity and then we do the theorem. So what we wish to show that the answer to this question is the answer we've been talking about and calling which is max over P of x, I of xy. Why do I write max here instead of supremum, which sort of covers some possible cases? Well, because this is a concave function of P of x. And P of x for a finite alphabet, that's a compact set. I mean, the set of all p's non-negative and summing to 1, compact set. And so the maximum of a concave function over a compact set, closed and bounded, is achieved. So this is what we're going to do. And now I'm going to give you the idea of the proof and the idea of the converse. I sort of like that. Wow. So idea for converse. It's looking ahead. You say, NR is the mutual information between W and W hat. Do you believe it? Well, it's less than or equal to this because the cardinality of this set is 2 to the NR when log of it is the upper bound on H of W. So the mutual information between W and W hat is less than or equal to NR. Excuse me? No, that's less. This is less than? Yeah. No. Oh, I see. You're saying this is actually greater than NR? Is that, yeah.
That's what you were just saying. Sorry, I
I should record what I say. Actually, it's being recorded for that.